Welcome back, everybody, to the Project Euler Refactor series. This is problem number 2 on the website, projecteuler.net. And we're going to take this old janky version here, and we're going to clean it up, make it look more professional. Because these were, you know, I was expanding my my skills, sort of solving problems with computational methods, as opposed to specifically working on my clean and you know, best practices in terms of you know, styling or spacing out my code and whatnot. So we're going to go over the refactoring first here, and then we're going to talk about how to optimize it or tricks for this particular problem. So, problem number 2. Each new term in the Fibonacci sequence is generated by adding the previous 2 terms by starting with 1 and 2. The first 10 terms will be, right? By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, find the sum of the even valued terms. Now, I almost tricked myself into thinking it meant the even terms of the Fibonacci sequence. It does not mean that. It means the ones that are actually even, right? So it means like this 2 plus this 8 plus this 34 plus whatever would be, you know, whatever the next even number is. So let's just be clear about that. So we're looking for even Fibonacci values. So when we run this original program, you can see we have this definition of the Fibonacci computation sequence as defined by this problem, right? So, well, I guess it's defined generally enough because we're including the n equals 0 term, where the problem is actually not including the first 2 terms for whatever reason they did that, but that's not a problem. Anyway, the first thing to notice is that I think this is what they did in Python 2. I can't remember, it's been so long. So, you know, we want to clean that up. You don't treat the return function like, or the return keyword like a function call any longer. There might have been a time where that was the case, but it's no longer happening. Okay, and we're gonna sort of tidy this up just a bit to make it a bit more readable. It's a bit tricky because I can't see my cursor with OBS doing its thing. Now, anyone paying attention to their loop mechanics can see that having a break here while having a true here, I mean, why would you even do that, right? So why would you not just kind of take this, right? Oh my goodness, I can't see the cursor. That's so ridiculous, right? And then just invert this so it's less than or equal to, and then we can just kill that break entirely because it ain't helping. And okay, but now we have a problem here that val is not defined initially, so we're just going to throw that down here. Oops, and we're going to, what are we saying? The original value is probably going to be, it doesn't even matter, it just needs to be defined. So we'll just say the original. And you can put these in the same line if you want, but you know, I don't do that typically just because it's clearer to individuate them. And there's some situations, you know, where if you try to define a bunch of variables at once, it's actually a hassle to separate them again. So I try not to do that. And, you know, some people prefer to have the spaces in here. It depends on how you want to, how you feel about how busy it is. You know, there's definitely a guide and options. You know, some people prefer stuff like that. I kind of like grouping certain things at the start all together, so it's clear that they're all sort of related to what's to come. It's almost like a header, as it were. But you know, there's probably best practices, and it's always good to investigate what the current paradigm is out in the industry. For example, you may notice I'm doing my best to keep all my doc strings or all my comments to about 72 characters in width. And that is just because that's best practices. And similarly in Python, you're supposed to kind of try to keep your code to the 80 character wide limit. So you might see me addressing some of that. Okay, so now where do we want to go from here? I'm going to save this out, and I'm going to switch over to a tidier version and see how much cleaner it gets. So as we can see here, it's more or less, I've tidied up the Fibonacci function again. I've, made this obviously a constant, and I've gotten all fancy here, and I inlined the definition of the val variable to use the walrus operator. And that way, I look like a total badass. As far as that goes in coding, right? So again, I mean, this is definitely clearer than it was, but is this as good as it gets? Let's be honest, putting it like this doesn't especially do us any favors, visually. Like, it doesn't make it especially clear. It kind of just takes the emphasis off of having to update val in the body of the while loop. And it does that by kind of, updating it and checking in the same iteration in the same line here. And as you can tell here, it only adds to the value when it's divisible by 2. It only adds to the total when the value is divisible by 2. So now there is a way to kind of clean this up a bit by putting that first, because you're always going to do that, and then you can just kind of go like this and say, okay, well, I'm not going to add. I'm going to iterate this loop. I'm going to skip this loop. When this is truthy, it's going to skip. So that means, divide this by 2. If there's a remainder, which is going to be 1 or 0, if it's 1, that's a truthy value. It's going to skip this iteration. It's not going to add that odd value to the total, right? And there we go. So that's that one. Now I've got timed versions. This is actually not that version that I want. Let's see. Well, let's see what it does. We're going to have to test the original first, actually. Let's see what the original does. There we go. So that's timed. We're going to block that out. So that's for just one iteration. That it took a whole 1.17 seconds. And so when I do the tidy timed version, I'm going to actually update it because I did that here. It's really hard when you can't see the cursor until like a certain point. There we go. Okay. Now what happens here? We get, this is actually 10 iterations, so we'll just divide it by 10 and it should be close enough. And it says, there we go. So yeah, it's about the same. So it really didn't save anything to do it that way, right? And that's actually pretty understandable. It has to do this check no matter what, more or less. And it does this every time, which is fine. It does that in both cases. So yeah, you can see how it wouldn't actually change anything. Now, does it look cleaner? I mean, perhaps. And I often, in cases where, you have to kind of do some work in a loop, just to see if you need to kind of execute the loop, sometimes it's better to do it this way instead of nesting the meat, the actual important part of the loop. Instead of nesting that, you actually kind of make it more important by not nesting it and letting the loop iterate here until it's ready to call the actual meat of the loop, right? So it seems a bit counterintuitive, but it enables you to do less nesting, which can get really dirty in Python when you're stuck with an 80 character width. Now, what if we want to try to make this a generator, right? We have a while loop and it's kind of ugly because of the walrus operator. And even if we took that out and put it back up here, it's not going to be super pretty. So let's see what happens when we use a generator. Okay, so, we just moved the while loop into the generator. And that kind of makes it look cleaner when we call it, right? So if you look here, we have now, this is actually a list comprehension, right? And you've got the filter if conditional tacked on at the end for the divide by 2, right? So that looks cleaner in the solution function, right? It's now just a single return of a sum. It's beautiful. But we did that by kind of pushing everything under the rug in terms of sliding it into this Fibonacci generator. There's really no reason to expect it to go faster. The whole idea behind putting it into the generator here is just to sort of make it look cleaner by moving the dirty sort of walrus thing into its own function, its own generator function, and then treating it in the meat of the solutions function like this, right? And it's clear because the function name is pretty explanatory, and we have the option to pass in whatever limit we want. In this case, it's just hard coded to be that constant like before. So you can see that it might be a little cleaner in implementation, but it's not actually faster. So now we can talk about the problem itself and how we might compute faster solutions. Because what you might notice about the Fibonacci sequence is that every so often there's an even number and there's a pattern to it actually. So you don't see it because they're not on here. There's a 0, a 1, and then a 1, and then a 2. So 1, 3, 5, whatever, 8. There's every third term is even, and the two in between those terms are going to be odd. So that's the pattern to the Fibonacci that I wasn't aware of. And so I started looking into how that can be used to sort of expedite the calculations. So you can see here, we find the pattern that we're always going to have the two evens or the two odds, and then those combine to make an even. But then you add an odd to an even, you get another odd. Then you add an even to an odd, you get another odd. Then you add those two odds, you get an even. So that's the pattern, and that's why it happens. So a bit of explanation there. So now this is the ideal solution, so called in the moment. You can see that I've updated the Fibonacci to use an inline Python ternary operator. There's really no particular reason for that. It was just like I just want to show it in one line. But it doesn't really do any favors for anybody. Now, you might notice that I've actually started on the first even Fibonacci number. So x, the second, x equals 2 gives the in this case, the second Fibonacci number, which is 2. And then I skip 3. And I don't know why I'm actually checking here. Why am I checking here? Let's go to the timed one. You shouldn't even need to check, actually. I don't know why it's doing that. Because it starts on the even one, and we're skipping 3, so it's going to be even. So let's just not do that. So that was something I must have overlooked somehow earlier. But you can see it's actually worse. So the ideal one, quote unquote, that skips 2 of the things, 2 of the calculations, which in turn calls to the previous 2. So you would think that this would save a bunch of calculations, right? But really, it still has to calculate pretty much every single Fibonacci number, because it's got to, every time it skips, right, it's still going to go into it and then call the previous 2 anyway, which is going to call the the previous 2 and the previous 2 and so on and so forth. It's actually, as you might have observed, anyone who's done Fibonacci before, that it's really redundant. So I have another generator version. Let's take a look at this one. Is there anything better about it? Well, this one lets you specify a start and end and a step. Now, that's pretty arbitrary, but it's just a little bit more generalized in a way. But in this case, it was just to kind of condense this up and make it look a little bit cleaner. I do not believe that it's any faster overall. So we're another 10 iterations of this generator version. So I kind of got lost figuring out improvements here, because there's quite a few, and I wanted to work towards the ultimate sort of, or the penultimate, I should say. Oh, this one's even worse. So look at that. In terms of utility, this generalized version of the Fibonacci sort of range, that's something. It's like a slightly more generalized version of the get and fibs function from earlier. It's fine in the sense that if you had to use it in more than one way than in the solution function below, that would be more useful to do it that way, right? But going back, there's something called memoize. That's the name that I borrowed when I learned it. But in Python, there's a built-in one called LRU underscore cache, I believe. I would look into that. But this is sort of what it does on a very simplistic level. It's a class that you initialize with a function. This call function, this call member function, is what makes it become a decorator down here, right? And so what we're doing is we're wrapping this Fibonacci function with a caching function called memoize. So what it does is it takes the arguments. If it doesn't have the arguments, it stores the arguments and the results of the function with those arguments passed. And then it returns that. So if it already has done this calculation, it spits it back automatically. So this is basically the same as the one before the generator function. I think that was the ideal. I called it ideal. And when you memoize it, what happens? Well, that was very fast. That was really fast. That was only one operation, but that was definitely less than a second. So now for 10 operations, 10 iterations of this solution being called, because of the caching, it now took, what was that? For 10, so that's going to be what? Is that 400ths of a millisecond? Am I crazy? What is that? It's very small. It's very fast. If I put into one iteration just to, because my brain is like not happening. So yeah, like to the power of -5. So I mean, -3 would be a millisecond. So -5, that's 22 nanoseconds? Microseconds. Oh geez, I was like, nanoseconds, that's insane. Okay, so microseconds. I forgot about micros. Wow. Can you tell I've been out of school for a while? Okay. So that's what happens if you cache it. But then it really kind of hit me because I've played some code golf. Code.golf has fun little coding problems too. And one of them was Fibonacci related. And I realized that there are ways of sort of optimizing those calculations. So I kind of, started falling down this rabbit hole. I'd already kind of realized the skipping of 2. Then I realized, okay, wait, this is faster to do one and, not skip 2. So instead of skipping to every third, this was actually faster. This is what's different, right? So previously, we're just updating the value with calling the x Fibonacci number. Geez, that's really, should have used n. So instead of calling the x Fibonacci number, we actually just do the Fibonacci summation in the value itself, right? So we take the previous Fibonacci value, we go to the next iteration, and we just add the next value to it, and that's our new updated value, right? So we're just kind of adding the next to the next to the next to the next, and that actually, because we're doing it, we're basically calling half as many Fibonacci functions. So that's why it's even faster than half, right? So it did a serious improvement there by not calling the Fibonacci function, adding it to another Fibonacci function, and just every iteration you're basically calling a whole slew of Fibonacci functions, right? So, the other version with the caching obviously still optimizes over this one, but this one, if you do need to have this Fibonacci function by the nth term and you want to use it, in this particular case, it would be faster to sort of like sum it as you go along each iteration in the loop. But that said, I remember my friend showed me another sort of fast way to do it in Python, and that's with this part right here. So it's straightforward. You take the next iteration of n, is going to be n plus m, and m is just going to become n, right? That's how you kind of calculate the next numbers. Similar story as before, right? If this is a truthy value, if there's a remainder, then we're just going to skip it, and if not, we'll add it. And this is timed as well. So how fast is that one? That one is, wow. Now look at that. That is comparable to the memoize function one, isn't it? What is this one? So that was 1, 2, -5. This is actually slower. So, this has to cache everything, right? So it has to insert things into a dictionary. It has to fetch them from a dictionary, which is, small cost, but it's still, it still exists. So now I thought about, okay, well, if we're skipping three numbers, which with each step, can we make it even faster? And so the sort of dirtiest way of doing that is to just hard code 3 steps into it and see how that goes. And that goes even faster. That's actually, yeah. So we're now into the single digit microsecond time range. Is that for 10 iterations or just the one? That is 10 iterations. So we're basically on the order of 1 microsecond now. That's how fast this is compared to the 1 second that was happening initially. And this doesn't use memowise. So, I mean, if you needed to use the Fibonacci function in some other context other than this solution, it makes sense to define the function as I have here and potentially use memowise to expedite the individual combination of terms. But in this case, because we don't have to worry about using the Fibonacci function elsewhere ever again, we can just kind of cram it all here and just call it multiple times to the update. So this just updates it the first time and the second time, and we can just change the initial conditions if we want. But we're going to talk briefly about maybe simplifying the summations, right? Because we're doing three updates of the n m values, right? So n is going to be sort of the second the higher Fibonacci number, and m is the one before it. So you sum those two to get the next term, which I guess you can call the oath term or whatever the next one would be. And so here's a process. You can kind of combine each of those steps into one, right? So you kind of you say the next n is going to be n plus m, and the next m is just n. And then that's how you would update it if you're just doing one, if you want to keep it separate. Whereas, obviously in Python, we've done the fancy double assignment thing to do it both at the same time. So then we take those next n values, and we plug it into the next n value and simplify. And we do that for both n, we do that for m, and then we do it a third time. And you see we have these sort of very simplified versions. So the next n will be 3n plus 2m. And the next m will be 2n plus m, right? And we can try that. So slower. It actually went slower. Now, not drastically, but the other one was 0.9. This is now 1.2, right? And basically what it boils down to is it's actually faster internally, for whatever reason, to perform each of these assignments individually, as opposed to trying to combine them and leverage any multiplication or division operations. I guess it's multiplication. There was no division. Right? And so there's other ways to sort of reformulate it too, so that you can kind of update them separately, see if that makes anything faster, which it does not. And what else can we do? We can try it the other way. So we can sum n and m first, and then we can kind of do an operation on n and m based on that. Does that do any favors for us? I mean, not really. It's at about 1.3 now, whereas you can say 1.0 or 0.9 is our best, right? And then what about this one? This one, 1.05. Yeah, that's not bad. Okay, so this is the same thing. We just picked the slightly later initial conditions, and we just calculate these one after the other. That makes sense. So that's probably about the same. That's actually the exact same, really, with one less iteration. Okay, well, what about this one? Okay, so if I can just kind of reassign it, try it this way. Again, it's just another way of sort of calculating each n and m. In this case, one then the other, or hold on to the old m, calculate the new m, and then with the old m, you can do this kind of slightly expedited function, and it's not faster either. So there we go. Believe it or not, it's somewhere around. Where is it? This guy. This is the fastest one. Why is it slow now? There we go. Okay, that was just a fluke. So there we go. That is our best solution, believe it or not. So, it really does depend on if you need to use the Fibonacci function outside of the context of the solution function, wherever the heck it's gone now. If you need to use it on its own, you might have to do it this way. But ultimately, if you are just going to have to, gun through a bunch of values and you don't really care about the actual Fibonacci function itself, then something like this is the fastest way to do it, because there's no multiplication, there's no complex mathematics, it's just straight addition. And that's like the easiest thing for registers to do on a computer. And so that is likely why this is the best solution. All right, so thanks for tuning in. And now we'll see if the answer is correct. How about that?